Hello, I'm Dr. G. Glad to see you at my channel. Today we consider the following problem. A hollow iron ball of mass m is placed in deep water. Find the buoyant force acting on the ball. The answer should be as complete as possible. In the beginning of solution, we place the ball in water, but we should decide first, will the ball float or sink? Usually the students use the following logic. They suppose that hollow ball is similar to a ship, which is also made of metal and is empty inside. So the conclusion is that the ball will float, and the students consider forces on the ball. It's two forces, gravity and buoyant force. The forces cancel each other, so buoyant force equal mg. And the students consider the problem solved. However, it is not so, and we will see why it is not so. The main reason why the problem is not solved yet is that we didn't take into account volume of the ball. We know mass of the ball, it is given in formulation of the problem, but volume is not given. In this case, we need to analyze dependence of solution on the volume. As a first step, we mention that mass and volume determine so-called average density of the ball, which is equal m over v. If average density is smaller than density of water, ball will float, and we have the case which we considered previously. If the average density is greater than density of the water, ball will sink, and the buoyant force will be given by this equation. There is also one specific case when these two densities are equal. In this case, we have so-called neutral equilibrium. It means that the ball can be at equilibrium at any point inside the liquid. In this case, again, buoyant force equal mg, and we can consider this case as a specific case of that case. What we need to do is just to change this inequality sign to other, and we have now two cases, case 1 and case 2. Before to proceed, we will find the volume which corresponds to equality of these two densities. We will denote this volume as V0. Average density in this case is equal mass over V0. This average density equal density of water. And from here we have V0. It is equal m over density of water. We can discriminate case 1 and case 2 using V0. If V is greater than V0, ball floats. If V is less than V0, ball sinks. We return to case 1. In this case, buoyant force is equal mg. We can calculate it. And we keep this value for further consideration. In case 2, buoyant force is given by this equation. Volume is not given, so we consider the volume as a variable. And we plot buoyant force as function of v. This is a straight line which exists for v less than v0. Maximum buoyant force is equal mg here. And v0 we can calculate using its definition, and it's given by this number. It's more convenient to represent this number in cubic centimeters. We use converting factor, and v0 equal to this number. However, at this point, the case 2 is not completed. Why it is so? Let's look to this case in more details. We have a hollow ball, and what will happen when diameter decreases? In this case, the empty space inside of the ball disappears, and the ball arrives at the smallest possible volume, which we denote as V1 and which is equal mass divided over density of iron. As a consequence, the value of V1 will be somewhere here. The corresponding value of buoyant force we will denote as FB1, and this part will be absent on the real plot. So case 2 exists only for V smaller than V0 and greater than V1. Then we add here the line which represents case 1. So the ball floats and buoyant force equal mg. And now we calculate all numbers which participate here. So here is our data. We calculate V1 using mass and density of iron, and we will have this number. You can check this yourself. And then we calculate buoyant force, which corresponds to this volume. It is equal 9.9 newtons. And mg, we calculated previously, equal 78 newton. Now, in the interval of v between v1 and v0, ball sinks. In interval v greater than v0, ball floats, and buoyant force is given by this plot. And now the problem is solved completely. We note again that in the beginning we didn't know the volume. We introduced this volume as a variable and analyze all possible cases. After this, we can say that the problem is solved completely. And don't forget, like, subscribe, comment, and hit the bell icon.